So throughout, stop me if you have any specific questions and I'll just whiz through. So mod 5, as you should know, is equilibria and acid reactions. And let's work through it all. Okay. And the notes are in the chat. Can everyone see those? They should have come through now. Okay. So starting at the very beginning, you have static and dynamic equilibria. So you should remember from the very beginning that there were these practicals you did to show reversibility. You had 4 case studies that the syllabus taught you, which was burning magnesium and burning steel wool. So you have metal combustion to show irreversible reactions. And you also had cobalt chloride hydrate and dehydrate, as well as iron nitrate and potassium thiocyanate as 2 pracs that showed you reversibility. So you should have the equations for both of these cases and an understanding of which ones are irreversible and which ones are reversible. The equations for metal combustion are here, and a short write-up of the prac is there. And then for reversible reactions, we know that they go forward and backward. The case study number 1 was the cobalt chloride hydrate and dehydrate, going from the pink solid to a light blue one by removing water. And the reverse of that is adding water back in and turning it back into the hydrated pink substance. So this is a case study you need. It's important to note that this is not the same as the COCl4 prac that you see later, which is also called cobalt chloride, but is not the solid form. This one is in a solution and is a dynamic equilibria. So the first one we see, this is just a reversible reaction. This does not form dynamic equilibria. Is everyone clear on that? We'll come back to the second prac a little bit later. And the equations for that are here as well. So understanding that the pink form has waters attached, as you heat it and remove water, you turn it into a purple, and then the purple turns into a blue solid. And in doing so, you've removed 6 waters for every single cobalt chloride hydrate. Okay. The second case study, iron thiocyanate, the equation comes up many times in the syllabus, but it first appears here. So you should recognize that this is a reversible reaction. It goes forward, it goes back, and it is a true dynamic equilibria. Okay. Any questions to begin? Okay, continuing on. Static and dynamic equilibria and open and closed systems. So we should know that in the whole universe is made up of lots of small systems, and relative to every system is a surrounding. So you consider any chemical reaction to be a system, and everything that is not that chemical reaction is the surrounding. And together, the system and surrounding make up the universe. When we talk about open and closed system, we're talking about, can this chemical reaction system exchange matter with the surrounding or not? And so for a closed system, matter cannot be exchanged. Open system, matter can be exchanged. And for both of them, energy can be exchanged as well. The only small caveat that some people might miss is an isolated system. So think about it as a sealed container that has a reaction happen inside it, but some surrounding material within that isolated system. That would be like a system with a surrounding inside an isolated system. So that's kind of the only weird case you might come across. But otherwise, for open and closed system, the definition is as you've seen.
Right. Isolated system is just theoretical though, right?
Yeah, in a way, but you can't really create a perfect isolated system in reality because you'll pretty much always have energy exchanging. I guess the best you can sort of think of is, imagine you had a thermos that was perfect and didn't let any energy transfer at all in and
Mhm.
out. That may be an isolated system, but even a thermos will have a little bit of energy transferring because the whole thing is not a vacuum.
Okay. Yep.
Okay. So then the important thing to take away for open and closed system, which of these can form equilibria?
Those.
Closed only. And that applies for both dynamic and static equilibria, which are 2 types we need to know. Dynamic equilibria, you have constant reactions going forward and backward at an equal rate, so a non-zero rate, whereas static, you have a 0 rate. So the forward reaction is 0, the reverse reaction is 0. The terms we use to describe dynamic and static equilibria, steady state and static state, are thrown around. We don't really use these too much. It's easy to just talk about it in simple words. So say one has a zero rate and one has a non-zero rate. It means pretty much the same thing. A dynamic equilibrium never reaches completion. A static does. Dynamic equilibrium is reversible. A static equilibrium is not. Double-ended arrow versus single-ended arrow. And an example would be Haber process as opposed to the complete reaction of graphite into diamond over time. You should have models for static and dynamic equilibria. So for a dynamic equilibrium, you may have done an experiment where you were transferring things from one container to another, and you had different rates of change initially because you did say one was transferring half and the other was transferring a quarter across. And eventually, once you did it a few times, so say you transferred 25 and 0 because this was half and this was 1/4. If you did that enough times, eventually you would reach a rate where the change or the exchange is exactly the same. So this was one way we could model it in the classroom. With any model, you should be able to talk about the limitations, including not being able to show constant exchange, no collisions, or no energy changes as examples. Then for static and dynamic equilibria as diagrams, you should be able to draw these in your exam and state why these diagrams model equilibria in the two different types. So for a static equilibria, and you imagine a system where you have black dots combining with white dots going to make black and white molecules. In a static equilibria, you represent the reaction going to completion. So the limiting reagent is completely consumed. All of the white molecules, or all the white dots, have been completely reacted and combined with black dots. If the reaction's gone to completion and it's not reversible, then there'll be no reverse rate, there'll be no forward rate, hence static equilibria. On the other hand, if you wanted to model a dynamic equilibrium, you only show two of the molecules, or three, or one. You basically don't show all of the limiting reagent to have been consumed. And you reason this as being because there is a reverse rate that is significant, and therefore the limiting reagent cannot be completely consumed if the reaction is not going to completion. So be able to draw this in your exam. Is everyone okay for pace, a little bit slower, a little bit faster? Thumbs up, thumbs down, or verbalize feedback. Good. Okay, cool. So, revision of mod 4, you should be familiar with Gibbs, free energy, enthalpy, and entropy. So you should be able to talk about what enthalpy is, talk about what entropy is, and talk about them quantitatively as well. I think what a lot of people miss with Gibbs free energy is what it actually represents. So we should know that a Gibbs free energy of delta G less than 0, this represents a spontaneous reaction, right? And to put it into words, what that means is that if a reaction has a delta G less than 0, there is free energy available to do work, and that allows the reaction to proceed. The ways in which you can have that free energy is if your enthalpy is negative or your entropy is positive. And whatever contributes negatively to your delta G is going to drive the reaction forward. So in the case of delta H, if it's less than 0, you have a forward enthalpy drive and it releases energy into the environment. And for entropy, if it is a positive delta S, this order increases. And in the context of delta G equals delta H minus delta S, these both contribute negatively. Okay. I think one thing that people miss a lot with entropy is how you figure out entropy change from looking at an equation. We won't worry too much about the laws of thermodynamics, not very important. Gibbs free energy equation, 4 cases for when you have spontaneity always, you have non-spontaneity always, or 2 cases where it's temperature dependent. These two. Any questions on those 4 cases? Okay. So then that brings us to Oh yeah, I guess one point before I move on to that. If you have a reversible reaction where the delta G, say in the forward direction, is negative, if you had the same reaction and you were looking at the reverse reaction, the delta G would be the same magnitude, but it would just be positive. And same with the delta H and same with the delta S. Everything will just be flipped in terms of the sign. Just one thing to note with equilibria. So then you have two case studies of non-equilibria systems that you're told explicitly that combustion is a spontaneous reaction that involves the burning of a substance in oxygen. You should know, therefore, that the delta H is negative and the delta S is positive, and that allows for the delta G to always be negative no matter what. On the other hand, photosynthesis, you need this reaction, so make sure this is memorized. You have a positive delta H, a negative delta S, and a positive delta G, therefore, always, no matter what. You should be able to look at any equation, like the photosynthesis one, and justify why it's a positive or negative entropy change. Can someone try verbally justify this one? Why is this a negative entropy change?
It goes from 12 moles to 7 moles.
The right idea, but we need a bit more
So
specificity.
so it has a reverse. Oh, I mean, yeah, it would have a reverse enthalpy drive.
We
I mean,
can't,
entropy.
correct, but when we're justifying, we can't just say 12 moles versus 7 moles, because what if the
Right.
moles are different states that have different entropy, correct?
Yeah.
So when we
Oh,
compare moles in
okay.
the equation, yeah, what was that?
Uh, well, there's the same amount of gas,
Correct, good.
but there's 6 liquid moles compared to 1 aqueous mole.
Good. So this is where the difference actually happens. Your entropy change is not through the change in gaseous moles, because you actually start with 6 and end with 6. You then say, okay, we have the same number of gas moles. Now I'm going to compare my liquid and aqueous moles, which are slightly lower in entropy. And you see you go from
So
6 liquid to 1 aqueous. Yeah,
so if we were to know the difference, one aqueous mole is like if you go from like one liquid to one aqueous, would that be more like entropic or less?
think of it as virtually identical, because the particle behavior is the same of liquid and aqueous.
Okay, sure.
So liquid and aqueous are pretty much one of the same, and it goes solid, less than liquid and aqueous, less than gas. And you
Okay.
just compare going down.
Mhm.
Good question, though. Okay, so that's photosynthesis combustion case studies. Keep those in mind. Don't worry about this, not necessary. And a few questions if you want to have a go at some. Also, don't worry about the relationship between temperature and delta G. That's extension. But if you are given this equation in your exam, you should be able to relate that delta G and temperature are proportional, and KEQ is part of that relationship as well. So I wouldn't say this needs to be memorized, but if you get in your exam, you should be able to talk about the relationships by rearranging the equation. Also not too important. Okay, to finish off here, we've got collision theory and explaining reaction graphs for concentration and rate change over time. So you should be able to look at any reaction, say that this reaction is reactants going to products. If you can explain what's happening here through the concentration and rate graph in words, then you've truly understood what's going to happen in collision theory for any reaction. So when you start with a lot of reactants and zero products, your forward rate is going to be highest and your reverse rate is going to be lowest at 0. Because there's lots of reactants and the forward rate is proceeding, this means that you're going to produce products over time whilst consuming reactants. In doing so, you've increased the amount of products, which increases the rate of collision between products, and you're decreasing the rate of collision between reactants because you have less reactants. And this continues over time in any equilibria, dynamic equilibria, to be clear, until you reach a point where you have equal rates of reaction and you have constant concentrations. And they are your two conditions for equilibria, dynamic equilibria. Equal rates that are non-zero and constant concentrations over time. Two conditions. Okay. So to summarize, first session, irreversible, reversible reactions, equilibrium types, static dynamic, systems, open and closed, enthalpy, entropy, Gibbs, being able to model dynamic equilibria, and finally collision theory to introduce it for the first time in an equilibrium context. Any questions going back? Okay. Second session, you have factors that affect equilibrium, which are, as we know, temperature, concentration, pressure, volume. And each of those factors you can explain through LCP, you can explain through collision theory, and eventually you can explain through Q and K. But for now, we'll just start with LCP and collision theory. So LCP definition, have it memorized. I think by now it's probably muscle memory. Just write that whole sentence out. Be able to justify, are you shifting right or left? If you're shifting right, you should know what that means in terms of rates as well as concentrations, and same with shifting left. When you structure LCP, if you have difficulty, then it's going to be a structure of three, where you start with the disturbance, you identify what changed. So for example, we added reactants and increased their concentration. You then go on to the resistance, where you justify with LCP. So you say the system will shift to counteract the change in disturbance in accordance with LCP, and you define. Important exam technique, the first time in your exam, and I recommend in the HSC, the first time in any response where you use LCP, you just rip the definition. It's 10 seconds, but it's worthwhile. And then you finish off your response by saying the shift. So you've identified the resistance. So if we increase reactant concentration, we must decrease reactant concentration. And the equilibrium will therefore shift to the right in order to do that. 3 steps, disturbance, resistance, shift. Makes it really simple for every single change response. As a small note, whenever you change concentration, you can never nullify the change. So you can never take the change back down to where you began. You can only partially counteract it. Yeah. This page pretty much sums up all the LCP shifts that you can possibly get. We should be familiar with increasing concentration. The resistance is just going to shift to decrease concentration. Remember that adding or removing solids and pure liquids, even if they're part of the equation, will not affect equilibrium, as the Q doesn't change. Adding solvents, this one is kind of a bit more left of field. You don't see it as often. But if you add a solvent, such as water, you are increasing the volume of everything. So you treat this for a solution actually the same as a volume change. So maybe take particular note of this one, as it's a bit rarer. But does that make sense for everyone? If you add solvent into a solution, you're increasing volume of the solution and therefore decreasing all concentrations, and you shift towards a side with more moles.
Wait, I saw a question where it said, I forgot what was added, but uh, like something was added and it like restricted the atoms from interacting and creating a reaction.
Is this the inert gas case?
Yeah, I think so.
Yeah, we'll get to that in a second. We'll get to that. Remind me when I get to it. So then going to temperature change, increasing, decreasing temperature, you shift in favor of the reaction that either consumes the energy to bring the temperature back down or releases energy to bring the temperature back up. You have two types of pressure, partial pressure, total pressure. Partial pressure is where you have a box. If there's only one gas in it, then the pressure of the system would be that single gas's pressure, and that's your partial pressure. Total pressure is the sum of all of the partial pressures of all the gases in a system combined and added together. When we talk about equilibria shifts, it's actually partial pressure that decides when we are going to shift one way or the other. And the shift to remember is increasing partial pressure of a single gas. You think of this the same as increasing the concentration of that gas, and so you will shift to decrease that gas concentration. If you increase the total pressure, you increase all of the partial pressures, and you shift to decrease the number of moles present in order to bring the total pressure back down. Two cases that are tricky involving inert gas, and those have been with us since mod 5 will have been drilled with this case because I absolutely hate it, and I hate when people get it wrong. There's the case of putting it into constant volume as opposed to putting it into constant pressure, and they're two different things. So to just clarify, inert gas means a non-reactive gas, which is not involved in the equilibria. If you're adding into constant volume, it's like putting into a box that is not going to deform. It stays the same size. When you add it into that box, are you changing the partial pressure of other gases in that system? When you add that inert gas in, we are not changing the partial pressures of any other gas. Their concentrations don't change. And because the Q value would therefore stay exactly the same, you would remain at equilibrium position, where Q equals K. So there's no shift in equilibrium if you add or remove inert gas from a constant volume.
Wait,
But
does this mean that the total pressure would be changed?
yes, that's the confusing thing, because everyone thinks that you add in inert gas, total pressure increases, and so the system shifts to resist that total pressure change. But that's not true because Q hasn't changed. And so you are still at equilibrium position in the system. Does that make sense for everyone?
So then how do you accommodate for the new volume of the gas introduced?
What was that? Sorry, Serena? I think I lost the start.
So how do you accommodate for like more gas introduced? Because you usually counteract that by, decreasing pressure or whatnot.
Yeah, nothing happens. It just stays at a higher
Huh.
total pressure, but the partial pressures all stay the same.
Could you clarify partial pressure, please?
Yes. So partial pressure is if you just have one gas in a box, say I have 300 kilopascals or 300 kilopascals of pressure from this red gas,
Yeah.
that would be the total pressure if that's the only gas in the box, right?
Mhm.
Say I added in 4 yellow gas dots, and this is 400 kilopascals of pressure.
Yeah.
If the 4 yellow dots were if the yellow gas was the only gas in the box, say there was no red anymore, the
Mhm.
total pressure of that yellow gas would be 400 kilopascals.
Yeah.
But when you have the red gas as well, the total pressure is the sum of these two partial pressures.
Yeah.
So the total pressure would be 700 kilopascals
Yeah.
in this
Mhm.
case. And when we talk about equilibrium shifting, we only care about the partial pressures in terms of volume pressure change. If the partial pressures are completely unchanged, there will be no shift. But if they do change, that's when you get a shift because partial pressure, you think of the same effectively as the moles of gas present. And these dictate how Q is going to change.
Yeah. Okay. I think that makes sense.
Yeah, it's a bit of a confusing one, but that's the way it is.
Wait, so if the total pressure changes, do all the concentrations just increase like proportionally to their ratios, or there's no effect on the concentration? Okay, they do.
Yes, they change
Yeah.
according to the ratio, and if the number of gas moles are the same on either side, then the ratio of gas change will be exactly the same, and there'll be no shift. But if you have one side that has more gas moles than the other, the ratio of change will be skewed in favor of the side that has more gas moles. So your Q will be affected more by the side with more moles on it. And that will result in a shift back into ratio after that.
Okay, so it's only partial change if the gas on each side is different, like the number of gas moles.
You will only have a
Effect on the equilibria.
You will only have a change in Q if the number of gas or the ratio of gas moles on the two sides is different.
Okay, yeah, that makes
Yeah.
sense.
If the ratio is the same and you change volume or pressure, the ratio of change will match Q or will match K, and you'll still be at Q equals K no matter what in that situation. Okay, Jake?
Okay, so if the volume was not constant,
Yes.
the addition of an inert gas would increase the volume, right?
It would increase the volume,
And then it
so
would just shift to the side with the high moles.
correct. if you have
Okay.
a expandable bag where it's constant pressure and the
Yep.
volume is variable, you treat an addition of inert gas the same as an increase in volume. And that's one of the favorite trick questions to hit you with, where it's like disguised.
Okay, so you just got to make sure you know what like the volume is.
Yes, you should know the situation. Is it a hard metal box or is it a expandable balloon or expandable bag?
Okay.
Yeah. And the only other thing they can ask you on is what is the effect of this on rate of reaction, which I think is what you saw in the question, Jay. So when you add an inert gas into a fixed volume, those inert gas particles take up space within the box and take up some of the collisions that would normally happen between the reacting system. So it actually
Oh, but the
slows,
rate,
yeah,
it would slow both of them, right? So
correct,
the equilibrium will still remain the same, but
exactly,
both of the rate of reactions will be reduced.
correct.
So how would you put it in a graph? Like,
Yeah,
will they just both go down and
yeah. So it's effectively if you had the two rates equal, well, two rates equal, and then you add inert gas, say here, you would just see something like this, like that, and then they'll be equal again.
okay.
Yeah.
So they never really change.
The
Like they never really differ from each other.
no,
Okay, cool.
in
Perfect.
effect, no. Okay, nice. Catalysts, no effect on position of equilibrium. They just get you there faster. So whenever you see the questions where they add catalyst, no effect on position, no effect on Q, no effect on K, you just get to equilibrium a little bit quicker because it speeds up both the forward and reverse reaction. 3 case studies, once again, have these in your back pocket. If you're going above and beyond, remember the delta H's, but that's like if you're going for the high band 6 and you really want to leave nothing to chance, but don't stress if it's if you still got other stuff to remember. I would say the colors are probably important for a reaction like the middle one here. So remembering that cobalt with 6 waters is pink, and then the cobalt COCl4 2 minus is blue. That will help you in a question when they bring up this prac, just to know what's what color. Okay. So that's its LCP. You should be able to justify these changes also through collision theory. Structure-wise, I recommend, once again, 3 steps. You talk about the disturbance and how that disturbance would change forward and or reverse rate. So if a concentration change, it's going to affect the rate on whichever side you've altered. If you increase the reactants, the reactant collisions are going to increase per second, and so you have a faster forward rate. The reverse rate will be unchanged. Then you would go and compare forward versus reverse, and you say, once I've increased my forward rate, the forward will be higher than reverse, and therefore, step 3, equilibrium is going to shift in the forward direction to re-establish equilibrium. 3 steps: disturbance on rates, comparison of rates, and then the equilibrium shift. And there's some sample responses here if you want to work through the wording of each of those. And there's a bit more on the inert gas cases at the bottom as well. Oh, yes. When you draw your concentration versus time graphs for any change, you should be able to identify each of the changes very easily. A concentration change has an abrupt change in one concentration. A pressure volume change is an abrupt change in all of the concentrations, whether it's all up or all down. And the temperature change will have no abrupt change in any of the reactants or products. And in all cases, you see a resistance. That tells you there has been some sort of shift. One important thing to note is when you have a pressure volume change, this graph is bad for one reason. It represents all of these concentration changes as pretty much being equal, but that doesn't make sense. When you make a volume change, say that I doubled the say that I halved the volume. What should happen to concentrations? If I halve the volume,
the concentration would double.
right, concentration should double for everything. It shouldn't be the same change abruptly. So if I was to redraw this graph in a way that I would draw it personally, This concentration at the bottom should double. This concentration should double above it. I'll do it in purple. And then finally, the top concentration should double as well. So these changes abruptly should be in proportion to the starting concentrations and reflect how much your volume changed. It is then the resistances that come after that are in ratio with the equation. So if the equation was 1 to 3 to 2, as we see in Haber process, the changes are in that ratio afterwards. Okay. So to summarize everything, and there's 3 sample responses, you can steal my wording for collision theory if you want to take these. So 1 for temperature, 1 for pressure, volume, 1 for concentration. And to summarize, LCP, collision theory, be able to discuss them differently. I cannot emphasize enough, at no point in an LCP response should you mention rate, ever. And in no point in a collision theory response do you talk about resistance, ever. They're completely different concepts that belong to each explanation.
Wait, what do you mean by resistance?
Yeah, so when you're justifying collision theory, you shouldn't be saying, say, for example, you increase temperature, and so the system would resist the change, and then you go into talking about rate.
Oh, okay,
Or
gotcha.
that. You would just straight away go into my change affected rates in this way. Forward and reverse reaction both increase. Because it's endothermic, the forward reaction rate increased proportionally more, and therefore my forward is higher than reverse. I'm going to shift in the forward direction to the right.
And the endothermic always, like for temperature changes more, right?
Forward, yes. And you justify it by saying it's got a higher activation energy.
Okay.
The endothermic
Right.
direction has a higher activation energy, and so is affected by temperature changes proportionally more.
Okay, cool.
And the
Thanks.
wording for that's all in the sample responses above. So steal it, please.
Okay.
Okay. Any questions there? We're halfway through. All right, let's keep going. K. Equilibrium expressions. You should be familiar with writing them based on an equation. So products over reactants. You take the concentration of each part and you put the coefficient as the power. And that's your expression. You never ever include pure liquids or solids, and you only include gaseous or aqueous substances that actually can have meaningful concentration. We should be able to tell from a big, moderate, or small K value the ratio between products and reactants. So if you have a massive K value of 1,000, it's essentially telling you that the product of the products is much bigger than the product of the reactants. And equilibrium likely lies towards the right, where you have more products compared to reactants. And vice versa. If you have a very small K, like 0.001, it means you have a lot more reactant concentration than product concentration once you've accounted for the ratios. And the benchmark is sort of a moderate K lies somewhere between 0.1 to 10. So if it's on either side of that, typically speaking, it's going to lie to one side of equilibria significantly, to either the right or the left. Examples of equilibrium expressions. So a case where we leave out the liquid, case where we leave out the solid. Okay. Reintroducing the main K and Q calculations, you should be able to calculate a KQ value if you have the equilibrium expressions, and you should be able to calculate equilibrium concentrations, and both these methods will require you to use iceboxes. To very quickly crash through an icebox, you have your initial concentration, change, and ending or equilibrium concentration. Oftentimes you are solving for the ending concentration so that you can insert it into a K expression and either solve for example, X, or if you have all these values that are known, you can then solve for a K. So they're your 2 question types. You're either solving for K or you're solving for X. So here's a question type. I'll give you all a quick moment to read over it. But to summarize, it's a question where you're given all the concentrations initially, and in the question they give you the ending concentration of methanol. Then it's up to you to determine the changes, and then you would be able to find the equilibrium concentrations of H2 and CO from those. Important to note in your change column, this is all in stoichiometric ratio. So the ratio here is 2 to 1 to 1, which is why the changes are in a 2 to 1 to 1 ratio. And subbing in those equilibrium concentrations into K, this gives you a 11.11 K value. Any questions there? Okay. A second question type is where you have unknown equilibrium concentrations, and you have to apply small change assumption. Small change assumption is basically where you have such a small K value that the shift right to reach equilibrium is super, super small. And when you compare any concentration against that change, the change is so insignificant, such as 0.000001, that you may as well just call it insignificant. And so in this situation, that allows us to bypass what would otherwise be it looks like it'd be a cubic in this case, and it allows us to get a much simpler solve without having to do quadratic formula or anything more
Wait.
complex than that.
Is quadratic formula not in the syllabus?
No.
Oh, because I've definitely used quadratic formula for a thing
Yes.
before.
Internally, yes, schools assess it. In the HSC, they cannot get you to do quadratic formula.
So every time it'll go to a quadratic, you know that's when you have to use small change assumption, right?
Pretty much in the HSC.
Okay.
That being said, if you want to be safe and you're just not sure on the day, there is nothing wrong with doing quadratic formula. It's still within reason. But for the state's accessibility, it has to be quadratic formula, but it has to be small change assumption viable if there is a quadratic formula. As long as you justify it. You have to have that sentence saying X is very small compared to blah because K is very small. Therefore, we can count it as negligible or something to that effect.
So would you lose marks if you do a quadratic formula?
I don't think so. But at the same time, like if it's very clear, then why waste the time?
Yeah.
So I guess it's, again, the game is all about risk mitigation. If you're really not sure on the day, you can just do the quadratic formula. But I'm like 95, 99% certain it will be just small change assumption. Like very certain.
Okay.
That's what I've
And
been told my whole
you
time.
can find that by looking at the K value, right?
Yeah. So in this case, the K value is 2.5 times 10 to the negative 6. KEQ less than 10 to the negative, like 3 was what we were taught back in the day. I think some schools teach it more conservatively as like -4 or even -5 now.
Yeah.
But just justify along the lines to make it suitable to the question. So like 10 to the negative 4, I think is pretty safe. Is if the concentration you're comparing against is like 0.0001, then it becomes somewhat significant compared to that number. But for the most part, the concentration they give you will be a much bigger number. Okay, cool. So there's some examples in here if you want to have a go at some, I guess, easier cases, but you'll find some better questions going through papers probably at this stage. Okay, introducing Q again. Q, same expression as K, but is experimental value, and you use it to test against K. So you calculate Q from having concentrations at any point, whether the system is or isn't at equilibrium. And the 3 cases you need to know is when Q is bigger, equal, or less than K, it tells you whether you're to the right, to the left, or at equilibrium. And you should be able to calculate that and compare to say that. So if you know you're to the right of equilibrium, this means your equilibrium position, imagine it on a number line, going from 0 to infinity. You have K somewhere along there, and you have Q. If your Q is to the right of the K, it means the Q is bigger than K. And in order to bring back down Q, you would have to shift the equilibrium left, because that would mean that you are reducing product concentration and you're increasing reactant concentration, which would bring Q back down. A shift left. Or on the other hand, if your Q is less than K, you would go the other way and you would increase your Q value back up until Q equals K and you establish equilibrium again. So I find the number line makes it really easy to visualize, but that's pretty much the gist of Q. So for any question where you get given concentrations, you should be able to calculate the Q value, compare it against K, and say, are you positioned to the right, left, or at equilibrium? And are you going to shift right, left, or stay at equilibrium? Okay. Factors affecting K, Q, and Q. You should know the only thing that affects K is temperature, and the other two factors, concentration and volume pressure changes will affect Q. Again, you can imagine it on a number line. So if you change your Q by changing concentration of volume and pressure, your Q will no longer be equal to K, and your Q will always return to K to reestablish equilibrium. This is the maths behind every reestablishment of equilibrium. Q will return to K. On the other hand, if you change your K by changing temperature, this is a different case where instead of Q moving and then coming back to K moves and Q chases K. K moves and Q chases K. So your equilibrium will always shift in a way to bring your Q back to K. Okay. We know these now as KSP and KA and KB, so we'll touch on KSP in a second. And the final thing in the third inquiry question is colorimetry experiment for finding KEQ. Really left of field part of the module where it's just bringing in colorimetry from mod 8. But now you know what that is, you should be able to explain the procedure of colorimetry. So at the start, just a very quick summary once again. You have a sample. If it's red, or in this case, they're pretending it's orange, blood orange, then you want to pick the complementary color, which is blue, because that is the wavelength that an orange solution is going to absorb the most. You select for that color by using a filter. You shine that blue light through the colored solution, and you find it absorbs a certain amount. I naught IT. By processing from the equation, absorbance equals log of I naught on IT. Is that correct? Yep, that's correct. I naught on IT. You would then be able to plot absorbances for known concentration samples that you measure. So you measure standard solutions and you can plot their concentrations versus their absorbance. You'd then be able to determine the concentration of an unknown solution. So say you now put an unknown concentration into the cuvette, say it reads 0.75, you can now read off of your graph that it would be 0.0006 as its concentration. Quick summary of colorimetry. So to actually find KEQ, they ask you to find it for the iron thiocyanate equilibria. The equation's at the top here. And the method includes selecting the right color filter. So if it's blood red, you're going to choose a green filter or a blue-green filter. You take standard solutions of iron thiocyanate and you create that calibration curve we just talked about, where you have absorbance versus concentration. You then combine known concentrations of iron 3+ and thiocyanate, which allows you to get an unknown concentration of iron thiocyanate, which is what you then put into the cuvette. To be measured, you find an absorbance, and you now have a known concentration. By putting these values into an ICE table, you can then determine the equilibrium concentrations, and by inserting those equilibrium concentrations in the KEQ, you can find the exact value. I won't spend too long on this because it's a little bit lower yield, but if you want another explanation, this link's actually quite good, and I'd watch into that one to get some numbers attached to it. As final comments on this, if you're trying to make an iron thiocyanate standard, you cannot just combine 0.01 molar of Fe3 plus and 0.01 molar of thiocyanate and say that, oh, it's going to go to completion, because it won't. This is an equilibrium system. It will not just turn to 0.01 mole per liter of iron thiocyanate. It'll actually be unknown. So the right way to do this, and there is a correction to these notes, you would do essentially swap Fe3 plus with SCN every time it appears in these notes here. SCN minus Fe3 plus like this. You would have an excess of SCN minus, and it is important you do that because it's colorless and won't disturb your colorimetry. And you have a severe limiting amount of iron. So much so that this will almost entirely be converted into Fe SCN2 plus when the equilibrium shifts right. And so you pretty much have a known concentration of Fe SCN2 plus from this procedure. To summarize, third session talks about equilibrium constant, K versus how big K is and what that means. Q versus K, Q always returning to K when you make changes to either concentration, pressure, or temperature. There's 3 weird uses of KEQ, or common uses now that we've gone through mod 5 and 6, and there's that KEQ experiment at the very end. So that's the end of module 3, or module 5, inquiry question 3. Solution equilibria to finish off. We should know that ionic dissolution takes place in 3 stages. It involves the breaking of water's hydrogen bonds, the breaking of the ionic lattice's ionic bonds. So this is the breaking stage. Does breaking bonds take in or release energy?
Take in.
Good. Takes in energy, so it absorbs. And then when you form bonds, this is spitting out energy. It's releasing energy back out. So the balance between the absorbance and the release of energy in dissolution decides whether it's going to be an exothermic or endothermic dissolution. And it can be both. So that's shown in these 2 energy profiles, where in the first one, you have a certain amount of energy input into the system in order to break all of the ions and molecules apart. And then when you form ion dipoles, that releases out a certain amount of energy. In this case, it's shown to be slightly greater. So this is your exo case. And in the other one, you release slightly less. And this is your endothermic case. Both are possible. Which one's more favorable? Which one encourages the reaction to be spontaneous? Which one would drive spontaneity?
Exothermic.
Yeah, the exothermic one. So if you have this case, you would say enthalpy is driving the reaction forward and it's driving the dissolution, driving the spontaneity of this dissolution. Okay. Beyond that, you can't just say enthalpy is the only thing contributing to dissolution spontaneity. There's also the entropy of dissolution, which is taking a solid mole and turning it into many aqueous moles, which most of the time is going to be an entropy positive process. So typically, entropy is driving dissolution, and enthalpy may or may not be driving, depending on the enthalpy change. So a bit more information about water's hydrogen bonds, which we now know will form because water is a polar molecule with OH and is bent. So you'd have to break those apart. That's endothermic. Ionic bonds are in the ionic lattice, so you have to put in energy to break those. And you form ion dipoles, which form solvation shells or hydration shells. So you should be able to draw diagrams similar to these, where you show the ion interacting with water and its oppositely charged dipole. So for sodium, if it's a positive ion, it's going to interact with a negative dipole on water, or vice versa. For chloride, which is a negatively charged ion, it's going to interact with the positive hydrogens on water.
Wait, are both the hydrogens in the water interacting with the chloride?
Yes,
Or
you
is
can
it just
draw
one?
it. You can draw it with both. You can draw it with one. I think actually probably drawing with both is better. I know in the answer one of the mocks it was drawn as one. I'd probably draw it as both if it was me.
Okay.
Yeah. Overall enthalpy change, we just discussed that before, but energy released minus energy consumed is the overall change. And to summarize, you form multiple ion dipoles around each salt ion, and so the energy required to break the bonds can be somewhat replenished, and the reaction isn't completely enthalpically unfavorable. It can even be enthalpically favorable if it is an exothermic dissolution. But overall, as long as your delta G is less than 0, that's when you have a spontaneous dissolution. And you have to be able to justify, is it enthalpically driven or is it entropically driven? And they can give you those numbers, for example. These diagrams are the ones I'd probably take. For the ion dipole solvation shells, draw either 4 or 6 waters surrounding the central ion. For the sake of time, probably just do 4. And we should be able to do hydrogen bond diagrams comfortably for mod 7 as well. Okay. Every solution you form is an equilibria. Every single one, even an unsaturated solution. An unsaturated solution forms static equilibria because you have completed your dissolution and your reaction stops. You've dissolved everything, nothing is dissolving back out. Nothing is dissolving in further. So you have 0 forward and 0 reverse rate. It is a static equilibria. A saturated solution, on the other hand, is a dynamic equilibria, where you have an excess amount of solid, typically, that is trying to dissolve in constantly, and it does. But then some of the ions that are in solution, once you dissolve some in, some of the ions will just precipitate back out. And it's a constant flow of dissolving and precipitating, which makes a saturated solution a dynamic equilibria. The key difference in the equations, therefore, is whenever you have an unsaturated solution, you represent dissolution with a one-way arrow. And whenever you have a saturated solution, it becomes a double-ended arrow because the reaction is then reversible or considered to be reversible. The only extra case is supersaturation. This is where you have more ions in solution than the solution can hold. And so your QSP would exceed your KSP. In this situation, you have precipitation of those ions coming back out in order to reduce your QSP and return to the point of saturation where the solution is at complete capacity rather than beyond it. So, yes.
If you had a saturated solution in equilibrium and the rate of the forward and reverse are like the same, and you add more solute, what would happen?
Nothing.
Okay, so, yeah, and like, what would the reasoning be for that?
My reasoning has always been because it's not involved in the Q expression, it won't change the concentration of ions in solution, and so your QSP will remain equal to KSP, and therefore there will be no shift. From a collision theory standpoint, I don't know if I can.
But like, if there was more in the like solution, wouldn't the concentration be higher?
Correct. Well, I mean, you have more solid, but is the solid part of the Q expression?
Yeah, that's true.
Right. So your Q doesn't change. Your Q would stay equal to K. But I'm not actually sure why, from a collision theory standpoint, you can't justify it. So I don't think you need to go there. Just say that your Q value won't change, and so you shouldn't shift.
Okay, sure.
Yeah. So I would have a go at this question for most of you, because I think a lot of you said this is not too comfortable. Have a go at this question later, where you try justify why the delta G is the way it is, and what are the processes involved with dissolving potassium chloride. So take a mental note or write it somewhere in your to-do list. There's an answer below to compare against. Okay, cycad fruit. Cycad fruit contains cycasin, soluble toxin. It is a carcinogenic neurotoxic glucoside. Don't have to remember that exactly, but just remember it has bad things. Maybe take one of those two, and you have to remove it before consumption. The method involves taking the actual fruit and removing the outer fleshy layer to get to the inner kernel. You'll then crush up those seeds, increase the surface area, which increases frequency of collision and hence faster rate of reaction. There's then two trains of thought of where you can go with this prac. You can either do it in a bucket or you can do it in a running stream. I don't care which one you take. Both are correct, but know that they're different. What's the difference between the two? What's the big difference? In either case, you're dissolving, but what's the difference?
like the running stream is like continuously new water, so it's gonna keep on dissolving without like, I don't know, kind of hard to explain, but like in the bucket, the cycad fruit is still gonna like be dissolving the cyclosin like within the bucket water. So it's still gonna be like in the system, I guess.
Good. So we're getting there. So how would you
Is it a different system in terms of like open, closed, whatever?
Good. So that's how you put it into the chemistry words. So Lily, you're 100% correct. You're saying that the stream is constantly removing the concentration, and that's because it is removing matter constantly by running it downstream. And so every time new water flows in, you are resetting the system to zero cyclase dissolved. And the constant removal of matter means that it's an open system. Whereas the bucket is a closed system. And eventually, if you're trying to dissolve the cyclasin out of the cycad seed, it'll reach a point where you have dissolved so much that you reach saturation point. You reach a dynamic equilibrium because it's a closed system. So that's the big difference between the two. Does that make sense for everyone? Open system versus closed. And so because the closed system reaches saturation point, in order to keep removing cyclasin, the workaround is you remove the saturated solution once you create it, which effectively reduces your cyclasin concentration back to zero and allows the equilibrium to then shift right again and dissolve more. So there's a process of getting to saturation point, removing the solution, putting in more fresh water, reaching saturation, removing solution, putting new fresh water, and continuing that over and over again until all the cyclasin is removed.
So would it be easy to just go with the stream example?
Depends on what they ask you. If they want you to discuss a dynamic equilibrium, then you're going to have to do the bucket one. But if they want you to discuss an open system of how you remove like something from solution or how you remove a soluble toxin, then you would go with the stream. So it's
Yeah.
situational. Have both prepared. They're not anything different to what you've learned before,
Yeah.
but just whatever's more comfortable. If you get the cycad fruit question, you go with that.
Sure.
Both valid. Just make sure when you explain the open system one that you're talking about how the constant removal of aqueous ions continually shifts the system right, and you don't establish dynamic equilibria. Okay. Any other questions on cycad fruit? All right. Solubility rules, needless to say. NAGSAG, PMS, Castrobear, whatever way you remember it, you have to have it memorized. Be able to investigate whether certain ions are soluble with each other. If you perform a test where you combine them together and there's a precipitate, it means they're insoluble. That's pretty much it. And there's 3 case studies listed in the syllabus: potassium chloride, silver nitrate, potassium iodide, lead nitrate, and sodium sulfate, barium nitrate. You should know the colors of these from Mod 8 now anyway, but there's a quick refresher of those equations that you need to know how to write those equations and sort of remember their colors. More important for Mod 8 though. Okay, let's finish off on KSP and solubility. So KSP, for any dissolution, involves a solid turning into multiple aqueous ions, 2 or more. The KSP does not include the solid because solid ions are solid and pure liquids are excluded from K expressions. Just a quick reminder as well that there are a few transition metals that you should know the valencies of: aluminium, zinc, silver, lead in particular. Iron, cobalt, copper are a bit more ambiguous where they should really specify the valency if they ever give it to you. And it should be unambiguous. But typically the valencies are shown there as well. The ones bolded are slightly more common. Molar solubility, should know this is how much of a solid you can dissolve in solution. And the molar solubility is the maximum number of moles in a volume of solvent. And it is a concentration, moles per liter typically. You can find the molar solubility for any ionic dissolution using KSP. You don't have to include an ice table when you're working, but I always found it easier to visualize what was going on if I did have an ice table. So depending on your level of comfort and experience, these questions include it or exclude it. Either way is fine. But this is the case where you get usually the x squared or 4x cubed and all those multiples going up depending on how big your coefficients are. Any questions on this question type? I think this is fairly common by this stage.
I just had a quick question.
Yeah, go for it.
I get confused when to add in, see there, it's like 2x
Yes.
squared. I get confused when to have that 2 or not to have that 2, like inside the bracket.
Good.
Like
Great
sometimes
question.
they don't use it.
Yes. So this is why I say an ice table makes it much easier to understand when you do have the 2 or 3 in front of the X. So in this case, we have barium hydroxide turning into barium 2 plus and hydroxide. The equation, I've made a mistake here. It should be 2OH and 2OH minus. And that makes it very clear that when you dissolve this imaginary X, which is the maximum amount of barium hydroxide I can dissolve in a liter, if I entirely dissolve that and turn my amount of solid into 0, the change in barium and hydroxide should reflect that ratio, the 1:2 ratio of the equation. So it's X and 2X. And that's where you know there's either a 2 or 3 in front of each number because it reflects the ratio of change from the equation. Does that make a bit more sense?
Yeah, that makes sense.
Okay, good. So then say, for example, if you had aluminium and aluminium sulfate, and you had this dissolution, you would then know, having done many of these ice tables, that aluminium's concentration should be 2x and sulfate should be 3x. That's where it comes from. And that's why people can shortcut the ice table over time. Okay. Continuing on. Did I miss? No, this is fine. Okay. QSP versus KSP, being able to determine when you actually precipitate or not. 3 cases, once again, very similar to QEQ versus KEQ. If your QSP is less than your KSP, it means that your solution is unsaturated, because once again, Q is your experimental value where you test concentrations against K. It tells you, are you positioned to the right, to the left, or at equilibrium? And depending on the number, you can figure that out. So if your QSP is less than KSP, the solution is unsaturated, and more ionic solid would dissolve if you added it in. Importantly, this is what's different for QSP compared to QEQ. QSP will not increase up to KSP in the same way that Q normally comes up to K. If your QSP is less than KSP, it will just remain at a smaller value. It will just remain smaller. So think about it as if I sprinkle a little bit of salt into water, a tiny bit of salt into water, I'll have some concentration of sodium and some concentration of chloride. Say it's really small, 0.0001 molar of either. That concentration isn't just going to increase on its own. The only way you can increase Q is by adding more solute and dissolving more. At some point, you reach QSP equals KSP, where you have a saturated solution and QSP remains constant. So that's the point where you have enough solid and the solution cannot take any more. In the cases where you are super saturated and QSP is above KSP, this is where you have your precipitate forming. It's because your QSP is above KSP, and in this case, it does actually return back down to K, and it does so by shifting the equation to the left, forming more solid, and reducing how much aqueous concentration of each ion you have, hence bringing down Q. So 3 cases, once again, remember those 3. And there are 2 common question types you get using QSP, not exhaustive, there are more out there, but the most common ones are you going to form precipitate when you combine ionic solutions, which is basically if you combine 2 solutions which have different volumes, you need to find their new concentrations for the ions you're interested in after the dilution from a combined volume. And by subbing those concentrations into QSP, you can find out, is the QSP bigger than KSP or not? First question type. Second question type is the common ion effect. This is by far more common. So common ion effect, we should know, is when you're dissolving a salt in solution, say you have MgOH, dissolving into a solution that already contains magnesium ions in it, the solution or the solid will not dissolve as much compared to if you were just dissolving into water. And this is because you already start with a slightly raised concentration of one of those ions. It would not take as much solute to reach KSP. You can justify that through the Q justification I just gave, or you can talk about it through LCP, saying that the addition of these common ions would cause equilibrium to shift left and therefore precipitate out some of the solid that would normally dissolve. The questions themselves are basically just a slight addition onto the icebox small change question we did before. The difference being that when you sub into the icebox, you start with one of the product concentrations as non-zero. And from there, you end up in the ending column with one of the ending concentrations being not just X or not just 2X, it'll be something plus X or something plus 2X. And from there, you can apply a small change assumption to simplify your calculation to be non-quadratic or non-cubic. Okay. And that brings us to the end of mod 5. Took a little bit longer than I hoped. But to finish off on the final inquiry question, we talked about dissolution of ionic salts, determining spontaneity through enthalpy, entropy, and temperature change. Dissolution in terms of what an unsaturated, saturated, and supersaturated solution is. The cycad fruit, solubility rules, ionic solution, solubility product, ionic product, molar solubility, QSP versus KSP, and finally the common ion effect. So let's take a quick break because that was a fair bit. Any questions? Okay, let's take a 5-minute break and we'll come back. We might go a little bit over 4, so you have to head off. That's okay. We'll just go into the drop-in session time. So 5-minute break, reset, and bring up the mod 6 notes as well. See you then. Alrighty, let's get going again. 30 seconds. Yeah, we'll definitely go over indicators. And to start off again, everyone just type in chat 1 or 2 things they want to go through in particular in Mod 6, just so I know where to spend a bit more time. Okay, buffer's always a popular one. Okay. I'll just send back in the chat the ones that are DM'd. All right, cool. So I think that frames most of it. Let's get going again. So module 6, acid-base reactions. Start off with properties of acids and bases, nomenclature, being able to name them. I won't spend very long here. Just refresh the properties and bases just to have those fresh in front of mind. Only thing to remember is that citric acid is a unique case. You might have to spend a bit of time just memorizing that too. Indicators. You should be able to read indicators. The pH range, you should know that that is the transition range where you see the middle color. And on either side of that range is where you see either the acidic or basic color. We should know specifically that indicators are equilibria systems as well. So for any indicator, it is a weak acid and its conjugate base, or a weak base and its conjugate acid. And one of them shows one color whilst the other shows another. Whenever you add in either acid or base to an indicator, you'll reveal one of the 2 colors based on the way that equilibrium shifts. So say, for example, you place this indicator system into a acid. Let's say you place it into a solution that has lots of H plus. You place all of this in. The H plus is going to increase in concentration, and therefore the system will shift left in order to counteract that change, consuming the blue colored A minus and bringing back down the H plus to some extent, and therefore showing a redder color for the acidic situation. On the other hand, say that you added this into a system that contained instead OH minus, lots of base. This would be a case where the OH reacts with H plus to form water, neutralization, and instead the system is going to shift to the right in order to bring back up the H plus, which creates a bluer color whilst consuming the red. So an indicator works in the same way as an equilibrium shifting left and right, just depending on how much H plus or H minus there is. And actually, I should come back up to this table here. These 4 indicators are the ones you must have memorized. You should know their ranges, their colors, and their names. Okay. There's a red cabbage indicator prac where you have to make the indicator by boiling red cabbage. Only strange detail to remember here. I remember one of the questions in the HSC was about the boiling temperature. I think it was either 100 or 120. I think it was 120 degrees Celsius. You can't go above, or you denature the indicator. But apart from that, the procedure is there. Only thing interesting about this prac is that you see almost a spectrum of color beyond just acidic color, basic color, and transition range. It's like you get a spectrum across the whole almost spectrum where you go from red to blue and a pink in the middle, and you go from blue to yellow with a green in the middle. And there's a particular reason for this. It's because anthocyanin, the indicator you see from cabbage, is a diprotic acid, a diprotic weak acid, which means that there are 2 transition ranges going from red to blue and then blue to yellow. And depending on just how acidic, it will show more of the yellow or show more of the red or somewhere in the middle. So understand that's just why we have a few extra colors here. Okay. I think someone asked particularly for indicators. Jeremiah, do you have any other questions about the indicators? I think this is pretty much it. Okay, sweet. So going on, acid-base reactions, 3 of them. Acid-base makes salt water, acid carbonate makes salt water CO2, and acid active metal makes salt and hydrogen gas. Just remember those 3. Everyday applications. So my recommendation with these is you always take in an everyday application that you know very well and an industrial process that you know very well. The other cases, you should be able to understand what's going on. If you have all the cases, more than one, then great, perfect. But you only really need one to be able to rip when they ask you, explain one application of neutralization in everyday life and industrial processes. So you should have one of each. So there's antacid tablets, tooth decay, preventing it, and baking soda. The cases are outlined here. Make sure you have an equation as part of the case. That is essential. If you don't have the equation, it's not going to make sense what you talk about. Same with industrial cases. You can either do the acid-base spill treatment or treatment of wastewater. Either case, have an equation, be able to describe it, and talk through it. So those are all there. Neutralization enthalpy, I think a lot of people fall over here because you confuse these experiments with enthalpy of combustion or, basically enthalpy of combustion are the main ones this gets confused with. Whilst it's the same equations and pretty much the same approach, there's one important difference between neutralization enthalpy and enthalpy of combustion. Does anyone remember what that important difference is?
It's the N is the moles of the limiting reagent
For which one?
for enthalpy of neutralization.
Not quite.
Like the water.
Good, the
The
water.
moles of the water. Yeah.
That's what you want to say. It's the water, because the water may not be in a 1-to-1 ratio with the limiting reagent. It's the moles of water for neutralization enthalpy. As stated here, this is a typo. Moles of water, and it's per mole of water formed.
So for neutralization, it's always water, and for combustion, it's like whatever fuel's being burned.
Correct, because you're asking different questions.
Sure.
For heat of neutralization, it's how much energy released per mole of water. That's the definition of delta H neutralization. And for enthalpy of combustion, you're asking how much energy did I release per mole of fuel that I burnt. So that's why you take the N as the moles of fuel there instead. So
Sure.
be familiar with the 2 equations. Be very careful with your C. The most common mistake in these questions is people misuse 4.18 times 10 to the 3 with kilojoules, or 4.18 times 10, or 4.18 using it in joules. So be very clear on what units you select. And same thing with your mass. You want it to match your C. So if you're going to pick the version of C where it's kilograms, which usually is, and I would do it this way if I was you, to minimize the number of moving parts, your mass then has to be in kilograms. Or if you use the version of C, which I don't recommend, where you use it in terms of grams, then your M is going to be in terms of grams. The golden rule is you match your constants units. And if you do that all the time, you will not have conversion mistakes. Okay. So 2 examples here. I won't go through them, but if you want to have a go at some neutralization calculations, there's 2 here. Acid-base theories. Starting off at the very beginning, the only ones that are actually listed in the syllabus are Arrhenius and Bronsted-Lowry. I think it's still good, if I was you, to take in the earlier theories into the exam anyway, and be able to talk about how we actually arrived to Arrhenius in the first place, before you go into that response. The structure that you follow is to define the theory, how did it improve on the one that came before, and then how is it still limited with a specific example. So Lavoisier, he said that acids contain oxygen, give an example, but it was still limited because certain substances that did contain oxygen were not acidic. Davy then said it was actually substances that contain hydrogen that gave them their acidic property. He improved by including some acids that had hydrogen, but he still could not classify acids that did not contain hydrogen, whilst also including some substances that did include hydrogen, that did have hydrogen but were not acidic, such as methane. So those are the early theories before you get onto Arrhenius, who said that acids were substances which in aqueous solution ionized to form H+ ions, and bases were substances which in aqueous solution dissociate to form OH- ions, and ionize, dissociate, one and the same in how you use them. He also integrated the definitions to show us neutralization in terms of H+, and the improvements were he started to be able to explain conductivity, able to explain neutralization through his equation, but there were still significant limitations, such as acids which weren't in this HA form were not included, bases which weren't in the BOH form were not included, could not acknowledge the role of the solvent in how it actually reacts with the acid, could not explain why certain compounds do not contain hydroxide, could not explain acidic reactions which weren't in solution, and couldn't explain why certain salts were acidic or basic as well. So those are the main limitations of Arrhenius. Don't have to have them all, but at least take a few. So to finish off, Bronsted-Lowry came in and said, acid, substance which donates protons. Base, substance which accepts protons. And he acknowledged the role of the solvent, and that's something that is kind of thrown around. When we actually say you acknowledge the role of the solvent, what does that actually mean? Bronsted-Lowry acknowledged the role of the solvent. Why does that matter? What does it mean?
Is this because it won't just be in aqueous solutions?
Right. It is still in aqueous solutions, but in those
Like-
aqueous solutions, he acknowledged that there's a role of the solvent in creating acidic and basic properties.
Did that enable him to understand amphiprotic nature?
Right, that enabled that. And it basically just means that if you acknowledge the role of the solvent, it means that the solvent itself, such as water, is actually involved in the reaction that creates an acidic ion, hydronium, or is involved in the creation of a basic ion, hydroxide. So no longer is it this H+ just coming from an acid molecule all the time. It doesn't necessarily have to originate from the acid itself, or the OH doesn't have to originate from a BOH form. It could be that you have NH3 that can act as a base simply by NH3 taking a hydrogen from water. And that is the role of the solvent in acidic and basic property. is that it can react with acids and bases in order to make acidic ions or to make basic ions. Any questions on that? Because that's kind of the whole dot point, that the role of the solvent can be seen in Bronsted-Lowry for the next inquiry question.
Could you just repeat the role of the solvent stuff again?
Yes. So role of the solvent means that acids create an acidic property. So let's say you have CH3COH. Arrhenius said that the acidic property would come from the H that was inside of the acid. Just because it dissociated and was liberated, now you have a H plus that is acidic. But Bronsted-Lowry said it's not just that you have a H that comes from the acid and now you have an acidic ion. It's that the H from the acid reacted in a way to bond with water, and this hydronium ion is actually the acidic ion in solution. So the solvent has a role in creating hydronium. It has
Because
a
it
role in
reacts with
creating the acidic property.
Okay, yeah.
And that's kind of what it's all about. So whenever you're asked which of these is an Arrhenius or Bronsted-Lowry equation, you'd be able to see the one with hydronium is the Bronsted-Lowry one. Or in the case of bases, if you have OH, if you don't have OH in the base and you're still able to create OH as a product, then it's acting as a Bronsted-Lowry base, not an Arrhenius one.
Okay, so if we want, yeah, go ahead.
Oh, sure. Okay. I just had a really quick question.
Yeah.
When you're doing exams and they ask to show equations, can you do like the equation of like HA and stuff like that, or do they have to be actual examples with like actual substances?
Depends on the context of the question, but if you're just referencing Arrhenius or Bronsted-Lowry theory generally, you can show the general equation. But if the question has a stated molecule that you're talking about, a specific acid or a specific base, then you have to include that one for sure.
Okay, thanks.
Yeah. And Jay?
Yeah, so majority of the time when we're differentiating between Arrhenius and Bronsted-Lowry,
Yeah.
is it just fine to talk about like hydrochloric acid reacting with H2O?
For showing Bronsted-Lowry,
Like, yeah, like you know how Arrhenius we would talk about. Oh, actually, no. This would be better with acetic acid, right?
right.
So is that just like the go-to equation to use?
You can use, there's not really a go-to, you can use any acid as long as you show when it's acting as a Bronsted-Lowry acid that it's reacting with water, or you're showing that it's like you could show the non-aqueous neutralization. That's the other way you can show a Bronsted-Lowry acid and base. So the ammonia reacting with HCl as gases to make NH4Cl. That's a
Oh
good
yeah.
one to show that it's a Bronsted-Lowry acid and base because they are acting to neutralize each other despite not being aqueous.
Okay. Cool.
So you can use that case as well.
Okay. Yeah.
Okay. Cool. We'll come back to conjugates, but to summarize conjugate, one of them has a H, one of them has the same things minus a H. That makes your conjugate pair, where the one with a H is the acid, the one without a H is the conjugate base, and vice versa. Okay, some advantages of Bronsted-Lowry to finish off, and limitations before. There's a little bit about Lewis theory, but you don't really have to know too much into that. Maybe just understand what a Lewis acid and base is. That's probably enough. But they shouldn't really ask about Lewis acid and base. Okay, small summary table. And then we're on to the second inquiry question. Okay, conjugates. So you should know your conjugate pairs, be able to identify them. Proticity describes how many protons an acid can donate. So it's mono, di, or triprotic. It can donate 1, 2, or 3 protons. The important cases to remember are probably just citric acid being triprotic. Have to really memorize that one.
Okay, and do we just assume that, let's say we have like H2SO4,
Yep.
do we just assume that it dissociates or like ionizes to form two moles of H plus ions?
Correct. So for HC purposes, we just assume both ionizations are strong and
Uh-huh.
leave it at that.
Okay, cool.
It's not like that in reality, but that's the way we
Yeah.
read HC.
Okay, cool.
Okay. Cool. So I think someone mentioned amphiproticity. So the case that you have to be able to do repeatedly for amphiproticity is be able to show amphiproticity through two equations. So if you have any amphiprotic substance, the way that you do it is you take that amphiprotic substance, you react it with H3O plus in one equation, and you react it with OH minus in the other, in order to show that it can form, that it can act as an acid or a base in either case. It's advisable not to do H2O as what you react it with. It's better to do H3O plus and OH minus. Question in the chat is, for more than one ionization, I'll just copy it in. For more than one ionization, how do we calculate the Ka value? Is it adding the Ka values or multiplying them? I always get confused. That's a good question. I don't know if you can get asked that, because you would need to have two different Ka values, one for each dissociation. It's a little bit more complicated than just having one Ka. Do you have the specific question? I can go through it later, but you shouldn't really see this very often. If you have the specific question, I'd be keen to see it though. Okay, all good. And I think that's pretty much all on amphiproticity. There's two more cases, the dihydrogen phosphate one, as well as showing water as amphiprotic. And you can do either of those through these two ways. So that's all on amphiproticity. Acid strength, we should know a strong acid dissociates 100%, a weak acid dissociates anything less than 100%. You have 5 strong acids that you remember for HSC: HCl, HBr, HI, HNO3, H2SO4. And everything else you consider weak. This is the biggest misconception in Mod 6. So if this is still something that's troubling you, please try disperse it the next week. Weak acids and bases have the exact same ability to neutralize compared to strong acids, which are equimolar and have the same volume. Neutralization capacity is determined purely by the moles of protons available. So it's determined by proticity and concentration. Strength plays no role in determining how much an acid can neutralize. So if you had 1 mole of 0.1 mole per liter H3PO4, you will have the potential for each of these to dissociate into 3 H plus ions, and the maximum amount of base which can be neutralized is therefore 0.3 mole per liter, even though the acid is weak. And this is because H3PO4, say it only dissociates 1% even, 3H plus over time and PO4 3 minus. Say this is the summary of the dissociation of 3 H pluses. Every time that you neutralize an OH with an OH minus, you neutralize a H plus, the equilibrium will continue to shift right, making more H plus. And if you put more OH minus in, it shifts right, neutralizes, and you keep shifting right and decreasing your H3PO4 molecule concentration until there is none left. And you've moved all of it into H plus, which means even if an acid is weak, you can continually shift equilibrium right by neutralizing until you actually neutralize all of that weak acid, regardless of whether it is completely like very, very weak or if it's very strong. The amount of protons you can neutralize is determined by the concentration and proticity, and that's all that matters for neutralization capacity. Okay. This is very poorly understood. Strength of conjugate acid-base pairs. So if you look at any acid, any base, and you know its strength, you should be able to tell what the conjugate strength is. Or if you have any acid or base and you're not sure, you can compare it against its conjugate to find out its strength. So they're the two kind of trains of thought you have. The stronger an acid, the weaker its conjugate base, and conversely, the stronger a base, the weaker its conjugate acid. But for our purposes, there are 4 cases that we learn. If you have a strong acid, the conjugate is an extremely weak conjugate base. If you have a strong base, conjugate is an extremely weak conjugate acid. If you have a weak acid, the conjugate is a weak base, and if you have a weak base, the conjugate is a weak acid. Keep in mind that an extremely weak conjugate base is weaker than a weak base. They are different things. They are different things. So as the example that I always go through, HNO3 reacting with NH3, we know HNO3 is a strong acid. NH3 is a weak base. Therefore, their conjugates, NH4 plus, because this is the conjugate of a weak base, this is going to be a weak acid. And for HNO3, because it's the conjugate of a strong acid, this is going to be a very weak base. So the products that you formed, one is a weak acid, one is a very weak base. And hence the salt solution you made is going to be slightly acidic because you have a weak acid being made and a very weak base, which is virtually neutral. The very weak base or very weak acid is virtually considered neutral. So overall, this is slightly acidic. And that's how you determine the acidity, basicity, or neutrality of a solution that you form or a salt that you form. Okay. You should be able to draw strength versus concentration models. Strength just basically showing that either you completely dissociate or you don't. And concentration, you either have a lot of stuff or a little stuff, a small amount of stuff. So they're the two different sets of conditions you could model. You should be able to describe how you use a pH probe, talking about how you need to initially standardize it using distilled water at 25 degrees Celsius to have a measure of pH 7. Then you can measure anything based on that standardization. You can get the pH of anything by submerging it, and then between measures, making sure that you rinse it with distilled water in order to prevent any contamination and inaccuracy in your measurement. And you'll be able to measure certain household substances, 4 of which are important for us. We should know soft drinks are acidic, red wine is acidic, orange juice is acidic, aspirin is acidic as your case for a medical substance, or I think it's a medicine. So those are described in the syllabus. You should have some memory of what are acidic substances. And as a basic substance, just to give you as well, oven cleaner contains NaOH and KOH. So you can say that is very basic. Calculating pH and pOH. So we start to get into the quantitative part of Mod 6. pH, negative log of hydronium or negative log of H+, and you can rearrange that to find the concentration of H+ as well. Every measure of pH increasing or decreasing by 1, so if pH decreases by 1, that symbolizes an increase in H3O plus concentration by 10 times. And vice versa. pOH is the same calculation except for hydroxide concentration, and the same rule in terms of a change in pOH by 1 is a change in hydronium concentration by 10 times. The rule for decimal places for pH and pOH. pH and pOH are always left in decimal places from the least sig figs in the question. And this also applies for pKa and pKb. Whenever you have a P in front, they are left decimal places.
Would you actually like lose marks for it?
If it's the question they're marking for sig figs. And they
Okay,
only
yeah,
mark
true.
one question for sig figs in the whole exam. So the maximum
Yeah.
number of marks you can lose for wrong sig figs is 1. But like, why would you want to lose a mark?
But you would never know which question it is as well.
No.
So
So you basically just want to do everyone right.
yeah.
Yeah.
So for pH, it's always just a 2, regardless.
No, not always to 2. Not always to 2. It's to the least number of sig figs in the question stem. So if your 3 numbers in your question stem were 0.555, 0.10, and 1.23456, the
That's
least sig figs is 2.
Mhm.
And so that becomes how many decimal places you left it to. Say, for example, this was just 0.1 and it was 1 sig fig, then you would leave it to 1 decimal place, and so on.
Yeah, and if it was like 10, like which it won't be, but like if it
Yeah.
was, because like
Hypothetically.
for one of my catalyst trials, there was like a pH question, blah blah blah,
Right.
and there was a comment saying pH is always to, I think it said 1 decimal place. I'll have to double check what it said exactly, but it like
It
because
should be.
because I you followed like the general, what's it called, the significant figures rule.
Right.
Yeah.
Can you dig that up and try find it later?
Yeah,
And I'll just
sure.
look over it as well.
Mhm.
Okay. Cool. So relating pH and pOH, essentially, the relationship between hydronium and hydroxide concentration all stems from the autoionization of water, which is where water can react with itself in order to form hydronium and hydroxide, because it's amphiprotic. So water can act as an acid and a base in the same equation in order to form these two substances. You can derive from that a Kw value, which is your self-ionization constant or autoionization constant. And that equals to 1 times 10 to the negative 14 at 25 degrees Celsius. So the Kw expression is simply hydronium times hydroxide concentrations is equal to 10 to the negative 14. It's a very small number, so only a small amount of water is going to turn into these ions. That allows you to relate, once you log both sides, that pH plus pOH is equal to 14. And that's where the relationship comes from. Noting that this is only true at 25 degrees Celsius. And if you were to change temperature, as you may have seen in the 4th trial, for those of you who have tried it already, if you change temperature, you're going to change Kw. And it would shift equilibrium slightly. Okay. Cool. So using pH to find strength, you're able to actually relate pH to 3 different variables: strength, proticity, and concentration. If you're looking at strength, because the dot point wants you to conduct investigation to demonstrate the use of pH to indicate differences between strength of acids and bases. In order to compare strength fairly, you have to fix in place the proticity of the acid you're comparing, as well as the concentrations, because those 2 factors can also change pH. So if you fix the proticity and you fix the concentration, you are then comparing only the effect of strength on pH. So this is probably the most important case for the dot point. And so in this case, you would find the H+ concentration of HCl is larger than that for CH3OH, which implies that this is a strong acid, whilst this is a weak acid or weaker.
Don't we determine acid strength based on like pKa and stuff?
That's how you quantify it, but as an experiment, it's hard to find a Ka or hard to find a pKa.
Yeah.
So for this dot point, they just want you to have a very easy way to determine pH, to determine acid strength just from measuring pH.
Yeah, so just whether it's most acidic or whatever.
Yeah. So if you're comparing one versus the other, which one has a lower pH? And if it's equimolar and same proticity, then it must be due to strength.
And if it's a different proticity, we can't compare them directly, or
Yeah, it wouldn't be a fair comparison.
sure.
Yeah.
Mm.
So 3 factors that affect pH: strength, concentration, proticity. If you want to analyze any of those 3 and their effect on pH, you have to fix the other 2 as constant. Okay, we'll come back to conductivity. Neutralization pH as a question type. So very common question STEM where you have 2 solutions being combined. One's an acid, one's a base, and you have an excess of acid or base left over. From there, based on that excess amount, you should be able to calculate the pH and therefore find, or you'll be able to calculate the hydroxide or hydronium ions in excess and therefore go on to find the concentration and the pH or pOH by the end. There are 2 cases here you can have a go at if you want a bit more practice. And that brings us on to buffers. So I introduced buffers here because they are relevant to titration. A buffer, to define it, and this is a very important definition that you write at the start of every buffer response. Buffer is a solution containing roughly equal concentrations of weak acid and its conjugate base that's able to resist a significant change in pH when a small amount of acid or base is added. And it can maintain this equilibrium because of resistances through LCP that you can justify through LCP. The 2 cases of buffers, and I'll spend a bit more time here, is you can either have a basic buffer or you can have an acidic buffer. For a acidic buffer, say it's this equation here, where HA is a weak acid and it turns into A minus conjugate weak base. This would be reflecting the bottom case here, where you start with a slightly acidic pH, assuming that the weak acid is putting a bit more H3O plus in the solution. So if you were to add a base into this buffer, so OH minus, the OH minus would react with the H3O plus to make water, decreasing H3O plus concentration. Normally, that would cause pH to swiftly rise because you've dropped off the H3O plus concentration. But this doesn't happen, and it's because of the buffer. The system is going to shift to resist that change, shifting to the right, which decreases HA, decreases H2O, but brings back up H3O plus and brings up A minus. And this means that the change in H3O plus concentration is actually quite minimal. And so the pH only slightly increases. And this will continue for as long as you still have weak acid undissociated left. At some point, you react all of the weak acid, and there is no longer any resistance to this change, beyond which you now have complete neutralization, and the addition of any extra base is just going to contribute as OH minus, hence pH concentrate. pH is going to jump upwards. And this point at which you exceed the capacity of HA is your neutralization capacity. Any questions there so far? Okay. In the other case, if you have a basic buffer, say you have BOH plus H2O, or it doesn't even have to be OH, it could be B plus H2O goes to make BH plus OH minus or something similar to that effect. If you add in acid to this buffer, H plus, that's going to neutralize the OH minus, turning it into H2O. And the system normally is going to drop in pH because you decrease your OH minus concentration. But it doesn't happen because the system is going to shift right in order to replace the OH minus that you initially lost. So it brings it back up to basically where it began. And that means your pH moves sideways, doesn't decrease very quickly, until you hit a point where all of the base has been consumed. Change colors. All the base got consumed at this point, and beyond then, you are now going to decrease your pH very rapidly as you add free H+. And you have a similar neutralization capacity at which the buffer stops to act. Okay. Any questions there? Buffer mechanism.
Could you go through the carbonate one really quickly, like the blood buffer?
Oh, yeah. That's the very end. Actually, I may as well just do it together. Makes more sense now. Okay. So the blood buffer, there's a few different equations that they can ask you to talk about. So there's actually three. There's the one involving the gaseous CO2 turning into carbonic acid when reacted with water. Then you have the carbonic acid that can turn into bicarbonate and hydronium, and the bicarbonate can then turn into either back to carbonic acid, or it can go a step further and turn into carbonate ions. So depending on what the question stem asks you for, you may be asked to use these two equations if they want you to talk about the gaseous component of CO2, or they may just ask you for the bicarbonate carbonic acid buffer, where you'd only need these two equations. And sometimes you can see this top equation with the bicarbonate associated as a HCO3 minus plus H plus. You may see it all attached as one equation like that, or like three parts all attached together. So you basically just pick which one suits your situation, and you can talk through them once you've selected your equations. So let's say you pick, oh, yep, you go.
Is it fine to have water as a reactant? I just remember from like above it said not to have water on like the reactant side of the
Yes, it is.
buffer equation.
That's different. So that's different. What we said before was for amphiprotic substances to show they're amphiprotic, you don't want to include water in that equation. But in
Oh,
a
okay.
buffer equation, you take the acid and its conjugate and you react them both with water to show that they can create hydronium and hydroxide respectively. So you have something that can create hydronium, something that can create hydroxide, and therefore you can buffer changes in both directions. Does that make any more sense? Okay. So to explain how this works then, if you have a blood pH which drops below 7.35, you've gone into an acidic condition. You have too much H3O plus. So let's say that you took the top two equations to explain it through. You would say that you have too much H3O plus, therefore the system shifts left. This brings down H3O plus, brings down HCO3 minus, and increases H2O and increases H2CO3. In doing so, that increase in H2CO3 shifts the top equation to the left, increasing H2O and CO2. So the net effect is you've turned all that extra H3O plus into CO2 gas, which can now be exhaled by the body. And that is how we can buffer that acidic change. Does that make sense first for everyone? Going the other way, if you're saying that instead you're now in a basic state where you have 7.45 as your pH, equation 3, and in this case, you can pick equation 3 to talk this through. You could talk it through equation 2 as well, doesn't really matter. Let's say we talk about it through just equation 3. Equation 3 is going to shift left to counteract that increase in OH minus, brings us down, 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 up and up. That shift has reduced the amount of change that occurred to the OH minus concentration, and in making more HCO3 minus, the system could potentially shift the second equation as well. So if you want to talk about all three, you can link this to here, shifting left and shifting again, but I'd probably keep it simple. If you're going to talk about the third equation, you only really need to talk about that one in isolation. So that would reduce OH minus and pretty much reduce the change in OH minus in doing so. So pH wouldn't change. And the other buffer systems you talk about through the same way, as long as you have the equation set up. So for the ocean buffer, it's a bicarbonate-carbonate buffer, which does involve CO2 if you want to as well. But for the discussion of buffer, usually you just talk about the two equations. And for intracellular buffer, not many schools teach this, but there's two equations there as well that show both ways the buffer can act. Okay. Any other questions on buffers?
Could you just clarify how to approach the first one where it's like the double equation?
Oh, right. As in the
Yeah.
one where you have HCO3 minus this one?
Yeah.
Yeah. So same thing basically. Say that you have it's all gonna be down to how this H plus concentration changes, to summarize it. Say that you added H plus, that's going to increase H plus, shifting left to decrease H plus, increasing H2CO3. That increase in H2CO3 is going to shift left again to make CO2 and H2O and bring that back down H2CO3. So the net effect, if you're discussing through that first combined triple equation almost, is that you're going to shift everything left and make more CO2 in order to bring down H plus. Does that make sense first?
Yeah.
And if you're going to talk about it the other way, with OH minus change, OH minus, you're saying that the OH minus is reacting the H plus, which means the system will shift right to resist that, to increase H plus, increase HCO3 minus, and decrease H2CO3. And because H2CO3 decreased, that's a disturbance of the left equation, you shift right to bring it back up, and these go down. CO2 concentration goes down in order to bring H plus back in the solution.
And then what if H2CO3 is changed?
H2CO, good question. If H2CO3 is changed, I'd probably treat that as
Can it change? Like,
yeah, it can change. It can change. I'd probably think about that through the second set of equations and say that if I increase H2CO3, that's going to cause a shift to the right and make more H3O plus. That makes the most sense to me immediately. But actually, you could think about it in terms of both equations at the same time. You could say if I increase H2CO3, it's going to have to shift left in this equation to bring it back down, which increases H2O and CO2, but also shifts right in this equation at the same time to bring up HCO3 and up H plus. So you can really say it's going to shift both equations away from the H2CO3.
yeah, that makes sense.
Yeah. Okay. So jumping back, we were just through buffers, and this brings us on to titration. How are we all going energy-wise? Do we need a quick break? We okay?
Should be fine.
Okay, let's keep going. Soldier on. Titration. Question is, how are solutions of acids and bases analyzed? You then have titration, obviously, with a bunch of key terms. So spend some time just being very comfortable with each of these. The method is listed all through here with specific details included. Probably won't talk on everything here. So just have a good idea of what is important when you're selecting a primary standard, what's important when you're preparing a standard solution, what's important when you choose an indicator, when you rinse your glassware, when you prepare the solutions for titration, when you actually perform the titration, and finally, how you do the calculation. Are there any specific questions through that whole method? Anything that needs a bit more explaining? I think in particular, with the rinsing, be very comfortable with knowing how to explain the effect on the concentration that you would measure. So if you had rinsed the volumetric flask with, for example, the solution that it's meant to contain, how would that affect the concentration that you actually measure down the line. So you should be able to talk about that. And when you choose an indicator, it's all down to whether you're neutralizing strong acid, strong base, strong acid, weak base, or weak acid, strong base. And that helps you to choose methyl orange, bromoethanol blue, or phenolphthalein. Okay, conductometric titration. Conductivity is a property of having free moving charged ions or charged particles. It could be electrons too. In the context of a conductometric titration, it's free moving ions. So whether it's a metal ion, is it a hydrogen ion, hydronium ion, or OH minus ion? If you have those in solution, they create conductivity. The more ions in solution you have, the larger the conductivity, and the lighter weight the ions are, the more conductivity there is as well. So they're the main points that you talk through in terms of how it works. And we'll go through each of the graphs very quickly too. Come back to precipitation titration in mod 8. So you should be able to explain each of these curves. You should be able to explain each of these curves where you have strong acid, strong base, strong acid, weak base, weak acid, strong base, or weak acid, weak base.
Oh, Jeffrey, that's the wrong.
Oh, Jed, I think you're unmuted. Yeah, you're good. Okay, so talking through each of those, the important features on each are all numbered here for the titration curve and the conductivity curve. Same, same, and same. Are there any questions on specific parts of these curves? Or any of the curves that are particularly confusing?
Can you please go over the last curve?
Yes, absolutely. This one?
Yep.
Yeah. So for a weak acid, weak base titration, you have 5 key points. You have the starting concentration, where if you have a low conductivity, it's due to in this case, it's the acid being weak. It only partially ionizes, and so you don't have much H plus or A minus. Then when you add in your weak base initially, you see a slight decrease in conductance. And this is because a large portion of that free H plus in solution is instantly neutralized. So your conductivity drops slightly because your mobile H plus has been neutralized to some extent. But then from 2 onwards, we see through point 3 that conductivity actually rises as we neutralize. It actually rises. So what's happening here is you have HA and H2O, your weak acid in solution with, which is ionizing into H plus, H3O plus, and A minus. This is all aqueous, aqueous, liquid, aqueous. So this is what you have in your solution. And as you add in NH3, the NH3 contributes NH4 plus and OH minus once it's reacted with water. So this OH minus is coming into the equation and reacting with H3O plus as you go along. And as we've seen in the previous conductivity graphs where you start with a strong acid, that showed before that you would just decrease conductivity as you react out all the H plus. Does that make sense for everyone why it would do that initially? Because you're reacting H plus with OH minus, you're removing a mobile ion from solution, and so your conductivity decreases. But this is absolutely not the case in a weak acid, weak base titration, or even a weak acid, strong base titration. This is not the case because we have a buffer. We have a buffer that is present. So as you remove this H3O plus and decrease its concentration by reacting with OH minus, the system is going to shift to resist that change. It's going to shift to the right in order to form your OH minus sorry, your H3O plus again, going to increase your A minus, and it decreases your HA as you go along. So the net effect in all of this for H3O plus concentration, it barely changed. So your H3O plus concentration might have slightly dropped after all this, which would account for maybe a small drop in conductivity. But you see the conductivity rises. So why is that? It's because you're making A minus as well as NH4 as you're putting this NH3 into solution. So you're creating two mobile ions as you neutralize one ion that is basically replenished. This increase in conductivity is therefore attributed to an increase in A minus concentration and an increase in NH4 concentration in the case of ammonia. This isn't always true because you may not always get a cationic conjugate acid, but this is always true. You're always making A minus as you go through this dissociation continually until equivalence point. Does that make sense for everyone? That's the hardest part of this curve to explain. Any questions there?
What's salt hydrolysis again? Is that just salt turning into its ions?
Yeah, so don't worry about it, is the summary. But salt hydrolysis is where the salts you make from a weak acid or weak base being neutralized, they are weak acids and weak bases. So what they do is they form a slight buffer. And at equivalence point, the change in gradient is not just a direct corner. It ends up being a slight curve because of that buffer. That's basically all it is. You don't have to say that in your exam. Most schools don't even learn it. I learned it at some point. I just include it anyway. But just say that 0.4 is your equivalence point, and it's where you have complete neutralization of the existing weak acid in this case. Okay, and then 0.5 going on from there, as you add base, weak base beyond equivalence point, you only see a slight increase in conductance since NH3 is a weak base. And so will only form a small concentration of OH minus compared to a strong base, which is the only differing feature in this graph here, where when you're adding a strong base instead of a weak base, everything before then is exactly the same, explained exactly the same. The only difference is beyond 0.4, when you keep adding strong base, you have a much higher increase in conductivity because you have complete dissociation of NaOH. Okay, cool. So those are all there for you.
Wait,
Yes.
could you just explain part 4 again? Like
Yes.
0.4 again? Yeah.
As in the equivalence point?
Yep.
Yeah. So all you need to say in your exam is that when you see changing gradient is because you've completely neutralized all of the weak acid in solution. And that's it. Don't worry about the salt hydrolysis, is what I'm saying. But if you are going to talk about the salt hydrolysis, which I don't recommend, it basically means that you have salt ions in solution, which are weak acids and or weak bases, which partially resist that changing gradient. And it ends up curved instead of just a sharp corner, as we see
Wait, so
in
the salt ions would be what, NH4, right?
NH4 and A minus.
Okay, so you stop forming that.
Correct? Oh, hang on. No, you wouldn't stop forming NH4 plus. You would stop forming A minus because you have no HA left. Once you run out of this,
Oh, yep.
yeah, you can't form any more A minus. And you're just adding in NH3, which makes some NH4 and some OH minus, but not much because it's weak.
So you would just say that the equivalence point is due to the like reduced production of ionic salt.
Yeah, you can say it that way, but it's simpler just to say it's the point at which you've neutralized all existing weak acid.
Okay, sure. Okay,
Yeah.
sounds good.
And you can, if you wanted to, you can justify that the decrease in gradient is because you're not making any more A minus, as you're alluding to there.
Okay, cool.
Yeah. All right. Any other questions? Okay. I guess just beware. You can have diprotic and triprotic titration graphs. Just know that the transition or the equivalence points are where the gradient is the steepest. So in a diprotic acid, you will have two equivalence points with steep gradients. And in a triprotic acid, it's where you have steep gradients here as well. These are your equivalence points going along. Beware
Is
those.
this testable from the syllabus?
I would say so. I think it's reasonable. It's basically just a slight extrapolation of what you normally see in a titration. And I don't think it's
So
completely unfair.
so they can technically ask you that.
They can give you this graph. I think so.
Okay.
I think
All
it's
right.
so just be aware.
Okay.
But you'd read it the exact same as any other titration graph.
Okay.
Yeah. And then really weird case where you have a what was this again? Neutralization of a solution where you have a strong acid and weak acid at the same time. It's also potentially possible. This is much rarer, I would say. Okay, to finish off, neutralization models. You should be able to show how a strong acid and strong base react, strong acid, weak base react, weak acid, strong base react, and a weak acid and weak base react. And you can show this via Molymod kits. Very low yield dot point in my opinion, but still something to acknowledge. Ka, Kb, you should be able to derive these from the equations for acid and base association, same way you derive a K expression. From our knowledge of K, a larger Ka means that you have a greater ratio of hydronium ions compared to the unionized acid, since hydronium is the numerator and Ha is the denominator. Kb is same. If you have a greater ratio of hydroxide to conjugate acid, that would suggest it's a larger Kb. Question in the chat is, how do you derive the Henderson-Hasselbalch? I'm going to be honest, I don't know because I never used it in my exams. And I would say you probably shouldn't use it anyway. But if you do want to do that, I think search online. I'm not the guy to teach you it, unfortunately. Fair question though, if you do want to use it. pKa, pKb. So understanding it's negative log of Ka or negative log of Kb for either of those. And the relationship between Ka and Kb is that a large Ka correlates to a negative pKa. A small Ka correlates to a small positive pKa, and a smaller Ka, which is much less than 1, would be a very large positive pKa. So they're inverse. As Ka gets bigger, pKa gets more negative. As Ka gets smaller, pKa becomes more positive. I guess the question is, yeah. You should just understand what does Ka actually mean. So big Ka just means you dissociate into H plus more freely, as opposed to a small Ka. Relating these together, Ka times Kb is actually equal to Kw. And so that's why it's 1 times 10 to the negative 14. And pKa plus pKb is equal to 14. And this is only true at 25 degrees Celsius. Common question type, where you have to calculate pH from a pKa or Ka. Good question to try here if you have time in your hands. Acid-base analysis. They say explore acid-base analysis techniques that are applied by industries, Aboriginal and Torres Strait Islander peoples, and using digital probes and instruments. So just have one of each. You need, for example, wine industry for determining the acid content of wine, pharmaceutical industry for finding the content of aspirin. This is where we introduce the back titration. So typically when you hear aspirin in a question, that's your signal to think maybe it's a back titration, but you should be able to tell from the question stem anyway. to quickly outline the back titration method, I think this graph or this diagram really helps you to visualize it. You're adding in a known amount of base, known excess base, into an unknown amount of acid. So unknown acid. Therefore, all of the acid will be reacted. All of it. And you'll have an unknown excess of the known excess base. So the known excess base, we knew how much we had, but we don't know how much of that excess is going to be left over after we dump it into the unknown amount of acid. So then what you're actually titrating in a back titration is the excess base that was left over as excess. So you put in, you're using your titrant, which in this case would be a acid titrant, putting it in, and you would stop when you've neutralized all of the base, and this would now be a known volume and concentration of acid. If you know that volume and concentration of acid, you can find the moles, which allows you to find how much base you neutralized. And if you know how much base you neutralized, then you can now know how much excess of the known excess you have. So now it's a known excess of the known excess base. And to work back, you can take the known excess base at the very beginning and say it was 9. And now you know how much was left over, minus 3, tells you how much base that reacted with acid, with the unknown acid initially. And that allows you to now find that based on whatever ratio it's in here, it's a 1-to-1, that, okay, I had 6 acid molecules in solution to begin with after going back through this titration. Does that make sense for everyone? So there's a sample calculation here. Again, I won't go through whole calculations, but there are answers to work through as well if you want to have a go at these. And you need to have an Aboriginal and Torres Strait Islander people's acid-base analysis example. But I think this is very, very far-fetched dot point, because even in the textbooks, they give you like applications. It's not really analysis. So I would sort of slot this together with the applications you talked about earlier. Plain ochre as stomach acid neutralizer, treating stings by neutralizing them or using soap tree as antiseptic. 3 examples, probably just take one. And then we talked about digital probes and instruments earlier. Also mentioned buffers earlier too. And that is all for module 6. Okay. Any questions? Going back
So
through?
for the Aboriginal and Torres Strait Islander people, would we just like is it fine like if it says like give an example of an acid base like use from the Aboriginal and Torres Strait Islander people, can we just say like soap tree? Is that just fine?
Well, you would have to justify it.
Like you would give a equation and stuff, right?
Yeah. So you'd pick one that's easy to justify.
Yeah.
I really like the antacid one because you can use that one as the medical one too when you probably talk about it there. So that saves you a bit of memorization work. I think that's the easiest, but you just need an equation and to explain how it's actually an acid-base application.
Okay, sure.
Yeah. Any other
That
questions?
makes sense.
Anne Maria, Chris, Jeremiah, Serena, any questions? And Arian too.
What was that?
Any questions?
Mine are mostly for mod like 8, so I'll
That's
probably
coming
do
up
it
soon.
tomorrow.
Cool.
Yeah.
Alrighty. Well, that's pretty much it for mod 5 and 6. It's been a long, probably very content-packed few hours, but hopefully that brought to light a few things to just revisit again content-wise. It's not meant to be super in-depth, but in your own revision, go back over these things, make a list of things that weren't entirely clear when we went through, and spend your time prioritizing those things to bring them up to scratch before Monday next week. So tomorrow will be similar for 7 and 8. Just crash through the whole thing. And if you have any questions, feel free to stay behind now until 5, when I have my next class. So drop in session until then. If you have to head off, enjoy your afternoon, and I'll see you back potentially tomorrow.
Thank you.
Okay,
Thanks,
thank
Jeff.
you. See you
Yeah.
tomorrow.
All good. See ya.
Bye.